Jared Atkinson. I'm from Varus Group's Adaptive Threat Division. I used to say that I was the token defender at Varus Group's Adaptive Threat Division because I work with really smart offensive minds like Matt Graber over there. But since we've started hiring some more defensive people, so I have friends that aren't just breaking things. I'm the hunt capability lead there, so the concept of hunting is practicing the assume breach mentality in an enterprise. So the basic idea is you have a really large organization. There's somebody out there that probably wants to gain access to their network, steal data, do whatever they need to do. And if there's somebody that wants to get in, there's a very likely chance that they will be able to get in. And so our job is to go in and look through the network as if they have been breached and try to determine where attackers have been or if there is a presence of attackers. My background is that I was in the U.S. Air Force on the hunt team there from 2011 to 2015. Probably one of my more proud achievements is last year at Black Hat, which is a big hacker conference in Las Vegas. I won the Minesweeper Championship. So before PowerShell was my Microsoft love, Minesweeper was the original. I'm also the moderator of PowerShell.com's security forum, which if you have any security questions, please come visit and ask the questions. And I also develop Power Forensics, Uproot IDS, and WMI eventing, which are two modules that Matt and I will be talking about Wednesday. So if you're interested in that, we'll definitely be touching on it. I also really love forensic artifacts, which is what led me to talk about Power Forensics. So going forward, so I kind of want to set the stage for what Power Forensics was created to do. When you're looking at forensics in general, forensics is a very touchy word because it's typically the true definition has to do with law enforcement process where chain of custody is very important and all these different things that when you're responding or practicing the assume breach mentality in a 100,000 node network, you can't necessarily take the time that a traditional forensic investigator would take. Forensics has taken on kind of a colloquial definition that is doing hard drive investigation or analysis, or even memory analysis. So originally, back in the day, or even today in more law enforcement-y type circles, folks are actually doing the image methodology for forensics. So they'll take a suspected infected system, they'll take DD or something along those lines, make a bit-for-bit copy of that hard drive. They'll keep the chain of custody records. This is very good because it's kind of the gold standard for forensics for the past couple decades. Very repeatable, meaning that any analysis that I do, I can go back to the evidence and reproduce that analysis for like a court case, things of that nature, and it allows for thorough analysis. One of the problems is that a typical forensic investigation is typically going to take around 3 weeks or so for a single system. So like I said, you have 100,000 endpoints. You don't know if there's a bad guy there, but you need to be able to quickly make a determination of whether there has been some attacker activity. You don't necessarily have 3 weeks per endpoint. And you also lose volatile data if you haven't captured that. Then folks started going into this kind of collection script concept. So the idea is I write a batch script, and then I'm going to script out, use PSExec or something along those lines to script out a bunch of tasks. So maybe one of the tasks is collect all the prefetch files or make a copy of the master file table, things of that nature. I'm going to pull it back and then do offline analysis. So you're not taking a full image because, in a terabyte hard drive, not all, however many bytes that is, are really valuable from a forensics perspective. I'm just getting the files or data that's important for my analysis. The problem with this is that it's often messy, not forensically sound, right, Matt? And that's one of my kind of big pain points. And it often uses third-party dependencies, so things like accessing a file, parsing the artifacts, and support for remote capabilities. So you may use PSExec to get remote execution. You may use raw copy to copy off a file like the MFT, and then you have to use analyze MFT to parse the MFT. So there's tons of different tools that you're using that have to be all strung together, and they're not necessarily created to be put together in that way. So then we kind of move on to this live response, which is kind of the concept that I'm pushing with Power Forensics. So the idea is that you're able to quickly triage key systems in order to determine where you need to look next and determine if something has indeed happened that you need to investigate. And so the pros are that it's very fast, forensically sound in the manner that I'm going to be doing it. It's self-contained, so Power Forensics, the remote access, the file access, and the parsing are all built in, and they all build upon each other. The cons are that it's not repeatable. So unless you're taking a copy of that data, you're not going to necessarily be able to use this investigation in court. So this is more focused towards your advanced persistent threat or like nation state type attacks. So, China hacks company X. Company X isn't going to get China to extradite the hacker in order to, press charges, right? So ultimately it's about stopping them from exfilling data before they're able to reach their objectives. All right, so my solution to this is Power Forensics. So this is a PowerShell module for live forensic investigation. I chose to write it in C#, so it's a compiled C# DLL, a binary module for speed and things of that nature. Minimizes the use of Windows API, so that whole forensically sound concept. So attackers can use rootkitting techniques to basically lie to you if you're using the operating system's API. So let's say you want to look at the SAM hive, for example. If you're using the operating system to look at the SAM hive, somebody can basically intercept that request and they'll lie to you when you're trying to get data from there. And so I'm trying to parse it all on my own and not rely on the operating system, which can be tampered with. Currently, we're parsing NTFS data structures, so the new technology file system, which is the base file system for Microsoft Windows. And then Windows-specific data structures like the registry, the Windows event logs, scheduled jobs, prefetch files, so on and so forth. A couple design requirements that I had when I first started is it needs to be forensically sound. If you haven't noticed, that's kind of my thing. So meaning it parses the raw disk structures on its own. So all the parsing code is stuff that I've written myself, as opposed to using some third-party library or some built-in library. And it can't alter like NTFS timestamps, things of that nature. So you don't want to actually affect the data that you're dealing with. It can execute on a live running host. So that's really important. I don't want to make an image and then be able to have to investigate that image. I want to be able to do it on a live host without taking it offline. It needs to be operationally fast, which I hope I'll be able to show you that here soon. Lee really helped me on that. So I was at DerbyCon, which is a hacker conference in Louisville, Kentucky. Lee sat by me in a class taught by Carlos Perez. And we literally just kind of went through on the MFT parsing. I think it started at like 10 seconds to parse an MFT, and we got it down to 4 seconds. So Lee showed me a bunch of ways to kind of speed up the way that the code was running. Everything needs to be modular, and so things like, for instance, I have an invoke forensic DD commandlet, which is going to allow you to read from a raw disk. That capability needs to be built upon in order to, for instance, parse the MFT and so on and so forth. So everything is built off of each other, right? And then it needs to be capable of working remotely, which we're at the proof of concept stage with that right now, so we'll talk about that at the end. All right, so the first demo is the forensically sound demo. So I'm going to walk through kind of how you would actually parse NTFS and how Power Forensics handles it. So the first thing that we need to do is read from a disk or volume directly, right? And this is where the only Windows API is used. And so the Windows API that we're using here is the create file API, which allows you to create a read or write handle. In this case, we're doing read only. Read handle to a physical disk or a logical volume. So think physical disk 0 or logical volume like the C drive, for instance. And then we're using the file stream read method to read from that handle. This is an example of the pinvoke signature that I'm using for create file. And I'll kind of show that as we go. The first thing that you're going to run into when you start reading from the physical disk, it's kind of an eye chart, but just to show, is the master boot record, and we'll actually show how the code parses all of this in a second. The master boot record the key there is actually this partition table, and so by default the master boot record has up to 4 partitions. There's an alternate partitioning scheme called the GUID partition table, which is going to allow more than 4 default partitions. There's also ways that you can make the master boot record have more than 4. Ultimately, what we're looking for are things like the partition type NTFS, or the status, which is 80 bootable, meaning that's the bootable drive or the operating system drive. And then we're looking at the things like relative start sector and total sectors, which are going to tell us how much or how many sectors, a sector is 512 bytes, are taken up by this logical volume, right? And so now we know where, in this case, the C drive is, or whatever your operating system drive is. After that, we're going to look at, in the case of NTFS, we're going to look at the volume boot record. And so this is going to have tons of information about how you should understand the layout of that particular file system or that volume. And so we have things like bytes per sector, which in this case 200 hex, which is 512 bytes per sector. Then you have sectors per cluster, which are 8 times 200 hex, which is 4096 bytes per cluster. Those are just helping you understand the geometry of the volume. And then we have things like a pointer to the MFT. So MFT first cluster number, that blue one right there, that's going to tell us where the master file table is. And so if we follow that pointer, we then find the actual master file table, right? And this is an example of a single master file table record. Master file table is a metadata file, so it is a file that keeps track of all other files on disk, right? And so there's an individual record. Each record by default is 1024 bytes. If it's not going to be 1024 bytes, the volume boot record is going to tell you that. Inside of that, it's going to have a number of different attributes. So they're not really shown here, but we'll talk about them in a second. Each attribute, like for instance, the file name attribute, I'll let you guess what that keeps track of, right? It keeps track of the file's name. A file in this context is either a directory or an actual data file. And in this instance, in this image, we have a data file. So there's a data attribute which either contains the data for the file if it's a relatively small file, or it contains pointers to the clusters that contain the data for the file. And we'll talk about that going forward. All right, so this is what a data attribute looks like. This is for a relatively small file. We're talking so there's two types of ways that the MFT record keeps track of data. It can either be resident or non-resident. A resident data record is going to have the data within that 1024 bytes. And so as you can imagine, a file needs to be around like 600 bytes or less in order to be resident. And so in this case, this just says hello world. So the data is small enough it's fit within there. In other situations, there's going to be pointers that show you where that data is. And so this is an example of a non-resident data attribute to where there's these data runs, which it took me a really long time to figure out how those work. But ultimately what they're telling you is that, hey, at offset 68DC04 for 21CO hex clusters, there's data that's relevant to this file. And this is an example of a fragmented file, meaning that the clusters are not sequential, so they're spread out throughout the hard drive. So you have to understand that and then read them all in order. Then you have this guy. So directories don't have data per se, but they have information about files that are contained within that directory. And so that's what this index allocation attribute is telling you. It's telling you, in this case, you have, let's see, hello world.txt contained in there and a file named test. And then you would have to follow it back and figure out what the directory's name is, things of that nature. So we'll show that here in a second. Okay, so now we'll actually start going through this. Yep. Okay, so one thing that I wanted to show, I meant to show this a few seconds ago. So windd.exe is a pretty well-known, dd.exe is DD is the Linux capability disk duplicator. It's supposed to be able to make bit-for-bit copies. windd is a Windows implementation. One of the things that I wanted to show is that when we actually run git.pe, which is part of PowerShell Arsenal, something Matt wrote, we can actually look at the function imports. And so it uses create file in the same way that Power Forensics is using it. So the idea is that although we're using a Windows API to get access to the actual drive itself, you have to do that at some point. So if an attacker is going to attack Power Forensics, they're attacking windd the same way. So that's the one place where I think an attacker could kind of take advantage of the process, but it affects pretty much everybody equally. Let me just run this real quick. Clean up. All right. I've been practicing all the little, shortcuts and stuff, but I forget. All right, so I'm going to be using splatting, which for those that aren't familiar, basically we have a hash table. Each one of these represents an argument that we're going to pass to a commandlet. So in this case, we have an in-file argument, which has a value of // physical drive 0. And when we do the @ sign in front of the props variable, that's going to just splat that out there and assume that each one of those items in the hash table represent an argument. So just for readability purposes, we're doing it that way. So invoke forensic DD takes a few different arguments. So in-file is the file that we want to read from. Offset is where we want to start reading from. Block size is how many blocks or how many bytes at a time we want to read. And then count is how many of those blocks we want to read. In this case, we're going to start at 0, read the first block, which represents the master boot record, and then we're going to output it in hex so that we can kind of see what it looks like. So this is the master boot record for this hard drive, the physical drive 0 on this virtual machine. You can kind of see down here there's some error messages, invalid partition table, so on and so forth. this guy is the partition table, but that doesn't really make sense. I don't know about you, but I don't really want to look at that. And so what we can do is we can take that capability where we're reading that first sector, and we're just going to do get forensic master boot record. And so now I've interpreted it for you, right? You have a disk signature in there. This is the code section. It's actual like boot code that's going to be running when you first start up your system. And then there's 3 NTFS partitions on this hard drive. Okay, so going forward, we can then do, like for instance, select object dash expand property partition table. There's a partition table array, which is this guy. We just want to see the actual contents of that array. And so there's partition objects. So NTFS, we see that this one is bootable. It starts at sector 2048. This is all decimal and goes through to whatever that sector is, 10.26047. Okay, so another way to do this same concept is there's get forensic partition table. So kind of skipping past that select statement there, and it does just the same thing. That's what I wanted to show. Let's see. I don't know, Control I think. Okay. Yes?
What's the best way that you find to enumerate all of the like physical drive strings? Is there like a living class?
Yeah, there's a WMI class. I forget what it is, like Win32 physical disk or something like that.
Yep.
Yeah. Okay. So yeah.
The help file because I couldn't figure out.
Oh yeah, it's in the help.
Yeah, when I started doing that, I got to Jared and I said, none of my drives are called that, right? I have C and D, right?
Yeah. Yeah. And so to clarify the drive right now we're looking at the physical disks. C and D would be the logical volumes. So we're going to get to that point in a second. But for the master boot record in particular, we're not dealing with the volumes yet because we're trying to figure out where those are. Okay, so now I'm going to skip over this one command, but in general what we're going to do here is this was just showing, the command above was just showing, we're going to take the bootable partition and we're going to save that to a variable. So that's simple enough. All right, so that's what we're doing with the master boot record, right? So we had a string of 512 bytes. They were just garbly gook. We don't know what they were, but then we actually parsed them out and so that a human could understand what they were, right? Get forensic master boot record. So now we're looking at this again, and we're taking that partition 0, and we're looking at start sector, and we're going to read 512 bytes. So that start sector is the beginning of the bootable volume, right, or the C drive in this case. So when we read that, again, not very much stuff. What we do see up here is NTFS, which is a good indicator that we're looking at an NTFS volume boot record, but still not very much stuff to go off of, right? Let's go back to get. Luckily, there's a get forensic volume boot record commandlet, and in this case, we're passing it C colon, and then you just run that, and now we have the volume boot record object, and this is what it looks like. So we have things like total sectors of this volume, the number of hidden sectors, bytes per sector, bytes per cluster. We have the MFT start index, which is going to point us to, this is relative to the beginning of the actual volume itself, so the C drive. It's going to point us to the master file table so we can start understanding what files are on the disk and start doing forensics on those. So just for the sake of needing that later, we're going to store that. And then we're going to go down. We're done with the volume boot record. Okay, now we're back at the master file table. So we're just kind of doing the same thing, expecting the same results. Insanity. And so what we did here, let's go back up. So we're looking at the C volume now. So this is what June was talking about, //./C colon. And then we have vbr.mft start index, and we're multiplying it by the bytes per cluster. So because the start index is stored in clusters, we want to understand how large a cluster is. And then we're saying, hey, we want to take the bytes per file record, and we want to read one file record. So this is the MFT record for the MFT itself. Somewhere in here, you see $MFT is the name of the MFT file. So the MFT record for the MFT itself is always at offset 0 within the MFT. So we always know it's the first record. And so within that, let's go back here. We can now interpret that with get forensic file record, right? So now we see, hey, that's human readable, right? It makes a little more sense. There's some timestamps in there. It tells you who the parent record number is. So we see that its parent is record number 5. Which is the root directory. And then we're going to store that for use here in a second. Okay, now I just kind of wanted to show the different properties. So these are proper.NET objects. So we have powerforensics.ntfs.fileRecord object, and there's tons of different properties, more than we're showing. So I have a formatter which only shows default properties, but you can see a lot more if you ask. And so what we're going to do, for instance, there's an attribute property which wasn't shown originally. Let's look at that, and this is an array of different attributes. So here's that standard information attribute, the file name attribute, which has the MFT, the name of the file. And then we have, this is one of those fragmented files. So we have 2 data runs which we have to follow in order to find the data within the MFT file. Let's see, okay. And so that ends the master file table entry, right? So within that, we want to kind of start understanding these data attributes, right? And so this is that data attribute, just kind of showing that we have it there. And so we could use where object name is data. And then we can go ahead and look at, or store it. And then this guy would be, it's kind of a for each loop. For each data run in the data run array, I want you to basically store this or write it all out to a file. So invoke forensic DD also allows you to output to a file. In this case, we're just going to write it's going to go through, in this case, 2 times and write each time to that file. So let's do that real quick. And it takes a little while. All right, so now we can come back, and so I was writing out to ctemp MFT, and if we play that, we see that the MFT has now been written out to disk. So the MFT is a hidden operating system file, which you theoretically are not allowed to touch, right? You're not allowed to view the data within it. The operating system is doing that behind the scenes. It's locked because there's changes happening to it all the time. What we just did is we found where the data that is associated with that file resides on disk, and we read it and then stored it in a file. So we never touched the MFT, we just touched the data that is associated with the MFT. So kind of a roundabout way there. All right, so one thing we've been doing this the hard way, surprise. There's a bunch of methods that are associated with the file record object. One of them is copy file. And so we could have, or there's also a get content. I think that's what we're showing here. Let's see, Control I. Okay, so now we're just going to get content and store that all to the byte variable. And so a lot faster because we're not writing to disk. We don't have to worry about the I/O there. And then I just wanted to kind of show the fact, whoops. Oh, dang.
It's the quote.
Oh, nope, I put the wrong variable. I changed the variable name and then didn't change it there. Okay, let's see. All right, so they're all the same size. So that's just kind of showing that kind of 3 different ways to do, or 2 different ways to do it, and we're comparing it. We have the same data. Well, at least the same size of data anyway. Just trust me that it's the same data, I suppose. All right, so then I would just want to store, so previously we were looking at a single MFT entry. What if we want to just grab the entire MFT? This is the thing that Lee helped me speed up. So we're parsing the entire master file table. Right now for the C drive, takes about 4 seconds or so. And so just to kind of the wow factor, I guess, there's 305,000 entries in the MFT that we just parsed in 4 seconds. So now we can start going through that. We have all the data stored in a variable there. All right. Oh, I kind of jumped the gun. All right, and then so one thing I want to show is that the index into the MFT array is representative of the index into the MFT for that record itself. So for instance, if we look at MFT 5, or the MFT at index 5, we see record number 5, which is the root directory's MFT record. So just kind of a way to quickly go through the MFT there. All right, so now we have the root MFT record. I just showed that. So we need to start being able to understand how the directory structure is built out so that we could find, I don't want to just go through every single MFT entry to find where like the SAM hive is, because that's going to take forever. I'd have to pass all those through the pipeline, 305,000 records, that just takes a ton of time. So it's better if we start parsing the directory structure to quickly be able to figure out where like C, Windows, System32, config, SAM is, right? Then we only have to technically parse 5-ish records. And so I just stored this record into the root variable. And so now we can look at the attributes. We want to grab the attribute that's called index allocation. So there it is. It's another non-resident attribute, but this one is contiguous. So just to kind of show, there's only one data run, meaning all the data is stored sequentially. And so that makes life a little bit easier, I guess. And then we're going to store that. And now we can look at the methods here. And again, we have this getBytes method. And so we're going to use that to read the contents. And so this is kind of a little hack. I don't actually know why this is necessary, but PowerShell has a weird thing to where sometimes it doesn't know that what you're giving it is an array. So this is just the syntax to say, hey, I'm forcing you into being an array, so that it works cleanly with format hex. So we're going to run that. So basically what we're running is index, which is that the index allocation attribute, running the getBytes method, passing it the // ./c : so it knows what logical volume to read from. And then we're going to pass the output, which is just a byte array, to format hex. And so this is what it looks like, tons of data. The thing that I kind of want to point out is you have things like Windows, users, system32, system volume information. These are all records that represent the files that are contained within that root directory, right? So if you parse that out, then you'll start to understand what's going on with the file system. Okay, let's see. And that's the end of that. So at this point, we've talked about how to get from the master boot record all the way down to the MFT, and then started to figure out how we can understand what files are residing in what directory, so we start to kind of find our way around the MFT. All right. Okay, so what? What does this all do for me, right? Hey, I got another demo. So there's a weird bug that I just found that one of these things doesn't work with the ISE, so we're going to go through the actual shell. So what we're doing here is get forensic child item. So functions similarly to get child item, but we're doing it in a forensically sound manner. So we're using all that stuff that I just showed you behind the scenes. We're parsing all of it, and in this case, we're going to show the children of the C drive. And so in this case, we have, for instance, program files x86, users, temp, Windows, but we also have the hidden files that you don't see when you just use get child item, right? So we, $attrdef, which is record number 4. And so remember we had that $MFT variable that has everything. If we do $MFT and then look at the item at, or the object at index number 4, we would see the attrdef file. So we can actually show that real quick. And there it is, so C attrdef, right? So now we're starting to kind of understand what's going on here. All right. This is my first time using this little fancy demo thing. I just didn't want to type all this out, so bear with me. Okay, and so now we have get forensic file record index, and we're giving it a path, right? And it's going to do a lookup and determine what that index is, right? And so I don't use this very often, but just to kind of show that we can take a path and determine what its index in the MFT is. All right, and then, so yeah, I'm going to kind of speed through this, but get forensic content is similar to get content, but it does it in a forensically sound manner. And we're going to basically read the contents and then encode it in Unicode of the attrdef file, right? Again, this, we could kind of make out some strings here, so $attribute list, $standard information, so on and so forth, but there's a lot of stuff going on that we don't know what it is, right? And so, luckily, there's get forensic attrdef. And we give it a volume name of C, and it's going to parse it out and tell us all the information, interpret the information for us. So the attrdef file contains different attributes that you're able to use within an MFT record. So things like standard information or file name or data, so on and so forth. And there's a bunch of other ones that aren't used very frequently, but they're allowed or defined. All right, what is this doing? All right, so now we're going to do get forensic file record index for system32 config SAM, right? So we know the SAM has an offset into the MFT of 278072. Yes?
What's the SAM?
Yeah, so the SAM is the SAM hive. It's the registry hive that contains all the information about users and passwords and all that kind of stuff. So I'm going to show in a second that it's a locked file, and you can't just randomly go and say, hey, I want to read the contents of the SAM hive, but we're going to then do that, basically. All right, so, this is kind of weirdly out of order, but Lee really liked this. So you could take get child item and do like the C drive. So we're listing out all the children in the C drive, and then pipe it into get forensic file record, and it will give you the MFT record for each one of those files. So just kind of a cool thing to show how this functions correctly with typical PowerShell command list. Did you have a question? Okay, cool. All right, so, jumped ahead of myself. So right now what we're doing is we want to get the MFT record for the SAM hive, and we're measuring how long that takes. This is following kind of the directory structure so that we only have to parse out the things that we need to parse. And that took 587 milliseconds, so less than a second, about half a second. And then we're going to do the long way, which is basically get every single file record, and then we're going to do where object, and it took 5 seconds. So we're talking, I'm not a good math person, but 10 times as long to parse that out. So if you're not actually following the directory structure, then it's going to take much longer to get to where you need to go. And this is using like the .where in PowerShell 5, which is significantly faster than where object through the pipeline. All right, so now what we're going to do is use the built-in get content to try to read the contents of the SAM hive. And not surprisingly, it says, hey, this is being used by another process. You can't do that. Okay, well, if we can't do that, then we'll just do it a different way. And so we'll use get forensics content and read the SAM, and there's the contents of the SAM hive. Again, this might not mean very much to you, but things like if you're parsing, NK is like the header for the named key property, or like the VK is the value key. And so you at least can, if you're familiar with the registry structure, you at least see that this is representative of a registry file. So we're in the right track, or on the right track. So then we could do things like we're trying copy item. Well, hey, same problem, you can't copy it. But what we can do here is copy forensic file, just kind of showing that concept. And then if I get child item, we've copied the SAM out to, whoops, I did get child item on the wrong directory. Oh, come on. No. Oh, no, never mind. So showing that the SAM file is 65,536 bytes, the copy that we created was 65,536 bytes as well. So we're copying the same size. I would do a hash, but you can't actually hash the SAM because it's locked, right? So, all right, so now building on top of that, we can do something like get forensic registry key, right? So now we had that whole blob of registry data, which doesn't mean anything to anybody, but we're able to start reading the contents. So in this case, we wanted to look in the software hive, right? And this is the root of the software hive, every key in the root of the software hive. Then we could do things like interpreting a specific registry key to understand what it means. So a lot of people are familiar with like the run keys that auto start programs when you set them. And so we have get forensic run key, which is going to parse the MFT, determine where the software hive is, or the nt-user.dat hive, which is the HKCU hive. There's a nt-user.dat hive for every user on the system. The currently logged in user's nt-user.dat hive is the HKCU hive. But we're going to basically go through all of those and find any auto runs set to auto start in the run or run once keys. This takes a little while because it's looking through, apparently not. It's looking through like 7 different hives to get this data. But here we see, in this case, like I have VMware user process set to auto run, so on and so forth. So now we've taken that and we're starting to actually understand data on the hard drive that we can analyze and determine whether something's going on. Okay. Yep, so just again showing the fact that everything that's being output is a proper .NET object that we can manipulate, has properties and methods, so on and so forth. We also have, like, for instance, there's a bunch of timestamps, and those timestamps aren't just like strings, they're actual date-time objects. And so in this case, I'm showing the born time of the record for the MFT record for the MFT itself, and it's an actual date-time object with that you can manipulate the same way you would manipulate any date-time object. So that's the end of that one. All right, so we can look at all this data and start interpreting it, but what's that actually matter if we can't perform an investigation? So let's look at a situation. So there's a guy on Twitter, he goes by Binary Zone, and he lives in the Middle East, but he's produced a bunch of forensic challenges to where he has basically had somebody come in and hack a system, steal data, or do whatever they do, and then he puts them out there on his website. You could download them and then perform forensics or an investigation, kind of practice your skills. And so we're using one of his images. And so in this case, it's not technically a live system, but the same concepts would be able to be used against the live system. For the demo purposes, I wanted it to be static so that stuff wasn't changing and my code wouldn't get jacked up. So in this case, client does not provide us much information. They believe a web server has been compromised. That's great. That's probably more than you'll really get in real life. And they provide a forensic image. The investigator must find a temporal starting point. So where do we think that the investigation needs to start on a timeline? And then determine whether the web server has in fact been compromised, and if compromised, provide leads to incident responders. Oops. Oh, that's the findings. Okay, so going back. That first demo with start demo actually went okay. Let me clear this out here. All right, so one thing I like to do, so right now it's mounted as H. We're just kind of showing that there's a bunch of stuff, in the H drive. One thing that we key in on, and this, I didn't know this when I started, but the XAMPP directory is the directory that contains an Apache server. So I might be particularly interested in, since the web server might be compromised, I might be particularly interested in files in that directory. All right, so we're going to basically store the MFT. There we go. So this is for volume H now in particular. And then what I'm doing now is I'm storing all MFT records that are in the XAMPP directory, right? And so now we're showing that the MFT, it's a relatively small file system, but it has 62,400 files. And within XAMPP, it has 19,473. So we already reduced the scope of our investigation by 50,000 or so, right? So now we're kind of narrowing in because we have, in the case of my VM, we had 305,000 records. I don't want to look through 305,000 records. I want to look through 100 records at the most. And so we need to start kind of narrowing in to figure out where we're looking. All right, so one thing we could do is we could take the items, all the files that are in the XAMPP directory, and we could group them based on their date time, right? So when I install an Apache server, a lot of times I'll install everything at the same time. And so we can look for files that were installed kind of out of order or at a different time. And in this case, we see that 17,000 of those files were installed on August 23rd. And then we have on September 2nd and September 3rd a bunch of other files that were created, right? And so in this case, I'm going to store those in a variable real quick. And now I can start referencing, groups 1 is going to reference all files that were created on September 2nd in this case. I'm going to sort them by their FN modified time. And so that's the modification time of the MFT record itself, which is one of the more true indicators of when a file was created. And then, so as you can see, there's a bunch of session files. So quick Google will tell you that every time a session is established with that server, a session file is created, right? And if you look at the times, it depends on if this is Amazon's web server, but if this is just an internal web server, people probably aren't connecting to this 200 times in 1 second, right? And so that's kind of strange. Let's see what they did on the 3rd. So we see one last session, and then we see stuff like webshells.php and c99.php, phpshell.2.php. In the incident response field, if you see web shell, that's probably a really bad thing, right? So let's look at some of that stuff. So we're going to look at the session. This is the session that happened right before all those files were created. And so we see that the username here was admin, which might be interesting. And then we're going to read phpshell2.php. So just for time's sake, we're going to look at one of them. There's some weird stuff going on. We see an IP 192.168.56.102, which might be something interesting. We see port 4545 kind of going on. Let's go see what else is happening. So we found an initial pivot. Looks like something happened on the 3rd of September. So we're going to start building kind of a date window around the 3rd of September. So $start now represents the 3rd of September at basically 12:00 a.m. And then we're going to create an end point, which is 1 day ahead of start. And so this is really cool. Like one of the cool things about Power Forensics is that everything that's already in PowerShell, you could leverage, right? So in this case, get date, I'm just building a date window. And then I'm able to take the MFT. We already had that saved, but apparently we got it again. And then I'm able to filter down and say, hey, show me files that were, in this case, modified. How much time do I have? Oh boy, we're gonna hurry up. Around that time. And so in this case, we started with 62,000 and we went down to 22 files, right? And that's a lot better. So there were 22 files which were created on that day. So let's specifically look at those files. And so again, we basically don't see anything super new, but we see that session was created, and then we see some temporary internet files that have a reference to that IP address that we saw. We again see web shells, so on and so forth. I'm going to kind of speed through because there's some cool stuff at the end. Another thing that we are parsing is the USN journal. So the USN journal is the update sequence number journal, which keeps track of all changes on a hard drive. A lot of times this can be leveraged like by backup software to see what files have changed since the last time you backed up, or antivirus to make sure that it doesn't waste time scanning everything and only scans files that were changed since the last time you scanned with antivirus. But this gives us information about every file that was changed or modified or deleted, so on and so forth, over the past X period of time. Usually a USN journal will keep about 3 weeks of information. So we got to kind of be agile, but we have a little bit of leeway there. All right, so the USN journal by default had 12,000, and we got it down in that window to 8,000. Usually it's a much more drastic number, but because this is some sort of brute forcing going on, there's a lot of files that were created within our window. All right, so what we're doing is we're going to look at all the different files. We're grouping by file name. So we see a lot of activity was associated with servermanager.log. So we might want to look at that at some point. We see these weird named files, tmp, udv, fh.php. We can see all the PHP shell stuff. One thing that I'm interested in, because I haven't seen it before, is this guy, php3331.temp, right? I see that I just happen to know this, I would show this, but we're running short on time. This is the MFT record number for that file, so let's go check it out. All right, so I just read the contents of that file, and it's PHP script that does system and then takes a variable and runs the command, right? Like that's the most simplistic web shell possible, right? It's just gonna run any command that somebody sends to it. All right, so this is something I just added. So there's not a commandlet associated with it yet because I've been super busy recently, but basically what we're doing is we're taking the Apache access log and we're parsing that out. So we're gonna look at every time that somebody tried to connect to the Apache server. And so this is what an Apache access log looks like. We have things like the timestamp, the method that was used in the HTTP method, the status that was returned, you can get the refer, so on and so forth, the username. That one's not a very good example, but. All right, so now we're going to group them by HTTP method. And so in this case, post requests or the post method is how you put data up onto the server. And so I might be interested in looking at what data was added to the server. And so this is all the information. So just down at the bottom, you see c99.php and then act cmd. That might be worth looking into. Kind of a cleaner way to look at this is, come on. So we're just going to show just that request there. And so, instead of getting all the entire object, we're just looking at the request. And we see like this, the CMD, which means that somebody might have been executing something on a web shell. So then kind of the crux of the whole thing. So I've been doing all that analysis kind of in a vacuum, but I'm really interested in being able to, we're not there yet, sorry. I really want to be able to look at everything at the same time, right? And so I'm building a timeline that includes all the different inputs, USN journal, MFT, registry, so on and so forth. So what I do is in this case, I stored a file record object for that C99 PHP, and it's just in $record, right? But what I'm able to do is convert to forensic timeline, and it takes, because there's two different timestamps that are here, it's going to create two different timeline objects representative of each timestamp that's associated. And it's going to tell me, in this case, it was modified and changed. In this case, it was accessed and born. And so we can kind of start to get context around what's going on. So now what we do is get forensic timeline. everything's been building to this point. And so now we're building a timeline. Right now it's parsing the registry, it's parsing the MFT, the USN journal, the prefetch, something else that I can't think of, the scheduled jobs. I haven't added the Apache access log, but that would be really nice to add into this. And then so like this is just going to show the different source types that we're getting. So in this case, like LNK files, which are the shell link or like shortcut files, MFT entries, USN journal entries, registry entries were on this guy. And so now we're going to filter them down based on that the window that we're looking at. Okay, just showing how many timeline entries there were to 244,000. We filtered it down to 8,731, so that's a really nice thing. And then I was just in New York at a conference, and Doug Fink showed his import Excel module, and so I thought that was pretty cool. So timelines, like 8,700 objects, you're not going to be able to just go through like, you know, on the console. So export to Excel. If you use the -show option, then it's going to, hopefully I tested this, there we go. It's going to pop up Excel for you, and now you can like start going through. You could sort based on the timestamp and then start going through and look at what happened in chronological order and start to build context around that situation. You can see what registry items were changed. I think that's the end of this demo. Yeah, okay. So quickly, initial findings, there's some sort of brute forcing SQL map. If you look at the refer, there's a bunch of SQL map references. These web shells were created. Probably didn't mean to do that. Another thing that I've found that's kind of cool is this, Gorse is kind of a visualization tool. And so, oh dang, yep. I gotta figure out where that thing is, there we go. This is a pain in the butt. Come on, there we go. Does anybody see where my mouse is? There it is. Yeah. All right, so Gorse is a visualization. So basically I took that timeline and created this visualization to show us files that are being created, changes to the file system. And so as you can see, some stuff is happening down there, right? Something happened that's probably not good. That's that brute force with all those session files being created. And then we see over here in this, we see like webshells.zip and c99.php. It's just kind of a way to visualize the data as it's happening. Man. I gotta find my mouse again here. Come on, there it is. Hopefully this works. Oh man, oh well, we're gonna do it from here, just like this. Okay, so the future of Power Forensics, basically I wanna move into multiple file system support, so why not be able to parse the extended file system on Linux or the hierarchical file system on Mac or the FAT. I want to start writing parsers for like the SQLite databases or ESE databases. WinPE, so Matt Graber wrote a WinPE wrapper module that allowed us to basically create a bootable USB drive that has Power Forensics loaded on it. And so you could go up to a system, plug it in, and boot from that USB drive, and you would have a clean forensic environment that's on a 1 gig USB drive. And so, like for instance, it's in my pocket underneath the microphone, but it's literally right there. And then Power Forensics Portable, which is the ability to run Power Forensics on a remote system without dropping that DLL to disk. And so I don't know if we're going to be able to show this, but it's really a pain in the butt when that messed up there. Okay, almost there. Come on. Oh man. All right, so that's skills right there. Okay, so the idea behind this is that there is a function called get forensic file record portable. I think that's what it says. I'll walk over here so I can see better. Yeah, and so the idea is that this encoded compressed file is actually the base64 compressed encoded version of that DLL. We're loading that into memory. And then there's basically an API for Power Forensics where you could just use the .NET classes. So in this case, you can run get forensic file record on a remote system over like WinRM or PowerShell remoting without the dependency of that DLL being on the remote system. So you're only touching memory, which is a pretty cool concept. So that's that remoting capability that we're trying to build in there. Yep, and so that's the end of this. Unfortunately, at the end, everything kind of got messed up with the display, but If you have any questions, please feel free to see me afterwards, and I'd be happy to kind of demo the portable version or the WinPE or any of those types of things. Thanks, guys.